MIT researchers have designed a polymer material that can change its structure in response to light, converting from a rigid substance to a softer one that can heal itself when damaged. You can switch the material states back and forth, and in each of those states, the material acts as though it were a completely different material, even though it is made of all the same components. The material consists of polymers attached to a light-sensitive molecule that can be used to alter the bonds formed within the material. Such materials could be used to coat objects such as cars or satellites, giving them the ability to heal after being damaged, though such applications are still far in the future. Many of the properties of polymers, such as their stiffness and their ability to expand, are controlled by their topology, that is, how the components of the material are arranged. Usually, once a material is formed, its topology cannot be changed reversibly. For example, a rubber ball remains elastic and cannot be made brittle without changing its chemical composition. The researchers wanted to create a material that could reversibly switch between two different topological states, which has not been done before. The researchers realized that a type of material they designed a few years ago, known as polymer metal organic cages or poly-MOCs, was a promising candidate for this approach. Poly-MOCs consist of metal containing gauge-like structures joined together by flexible polymer linkers. The researchers created these materials by mixing polymers attached to groups called ligands, which can bind to a metal atom. Each metal atom, in this case palladium, can form bonds with 4 ligand molecules, creating rigid cage-like clusters with varying ratios of palladium to ligand molecules. Those ratios determine the size of the cages. In the new study, the researchers set out to design a material that could reversibly switch between two different sized cages, one with 24 atoms of palladium and 48 ligands, and one with 3 palladium atoms and 6 ligand molecules. To achieve that, they incorporated a light-sensitive molecule called DTE into the ligand. The size of the cages is determined by the angle of bonds that a nitrogen molecule on the ligand forms with palladium. When DTE is exposed to ultraviolet light, it forms a ring in the ligand, which increases the size of the angle at which nitrogen can bond to palladium. This makes the clusters break apart and form larger clusters. When the researchers shine green light on the material, the ring is broken, the bond angle becomes smaller, and the smaller clusters reform. The process takes about 5 hours to complete, and the researchers found they could perform the reversal up to 7 times. With each reversal, a small percentage of the polymers fails to switch back, which eventually causes the material to fall apart. When the material is in the small cluster state, it becomes up to 10 times softer and more dynamic. They can flow when heated up, which means you could cut them, and upon mild heating, the damage will heal. This approach overcomes the trade-off that usually occurs with self-healing materials, which is that structurally they tend to be relatively weak. In this case, the material can switch between the softer self-healing state and a more rigid state. Potential applications include self-healing materials, although for this approach to be widely used, palladium, a rare and expensive metal, would likely have to be replaced by a cheaper alternative. Another possible application for these materials is drug delivery. It could be possible to encapsulate drugs inside the larger cages, then expose them to green light to make them open up and release their contents. Applying green light could enable recapture of the drugs, providing a novel approach to reversible drug delivery.